Hey guys, welcome to the fourth installment of the integration topic in extension 2. Hopefully you've enjoyed the videos on integration up until now. So today, probably my favorite part where I get to show you some of the, I guess, special cases and some of the cool questions that you see in this topic now. This topic is hard, right? In that there's questions that fall under certain categories like partial fractions, by parts, trig, and then there are questions that have very little guidance and you just need to be able to apply techniques that you've learned. And yeah, like it's just random in some aspects. So that's what makes this topic quite interesting, is that you can apply the techniques that you've learned and somehow sort of break it down. So before I go and do those fancy questions that have no guidance, I want to show you a special case. Now, this case is kind of it's quite common, and at the same time, it's probably underplayed in terms of at school in terms of how common it is. So let me showcase the theory and then show you one or two examples. So maybe part one, I'll just call it maybe a special case. I have no better name for that. So let me give you the formula first, and then I'll prove it. So this one here, sort of a giveaway, is that it always comes with limits. So the integral of fx dx is equal to, now I call it the symmetry special case, right? Basically, whenever you have a limit and it's from 0 to a and you have it equal to 0 to a, the formula is if you take a function of a minus x dx, it's the same thing, right? So this formula is equivalent. Yeah. That's important. So we're going to prove this equivalence, right? So now maybe you can call it the symmetry case, right? And that's what I'll be referring to in this presentation. But the symmetry case is a special case of an example. So I'll put a little asterisk here because here's my proof. Right? The proof is really straightforward, right? So generally speaking, whenever you see this in the past paper questions, one or two things can happen. The more common thing is that you see part A, prove, part B, use. Sometimes you might see just use, right? But I'll show you what to look for in adopting this case. So let's start. So to prove this, what we're going to do firstly is to replace this, highlight that incorrectly, replace the inside here with a letter, right? We're going to use basically substitution or u sub to basically replace it. Yeah, maybe let it be v equal to a minus x, right? And the moment we do that, right, so we're going to prove that the left-hand side equals to the right-hand side. So let v equals to that. We're going to, because there's limits as well, we're going to do, I always call it the triple sub. We basically change the limits, sub v in, and also change sub the dx in. So first thing I'm going to do is to go dv equals to negative dx, then dx equals to negative dv. So I'm going to sub that into there. I'm going to sub v into here. And also, let's change the limits as well. So when x equals to a, v equals to 0. You can see that I use v and not u because I think a number of times my students chuckle when I say fu. It's not great, so I'm going to avoid that little scenario by using v. So that's purely why. It's not because I didn't want to use u, because u is usually the parameter of choice for substitution. So when that's 0, v equals to a, right? So cool. So triple sub, right? So the left-hand side then, which currently equals to 0, a f of a minus x dx. The moment I sub in, I'll sub in 1. Sorry, I sub in v, this guy, these guys, right? All into 1, 2, 3. I get new limits of a to 0, f of v multiplied by minus dv. Now, the number of times my students tell me, teachers don't show them that whenever you have a negative, when you're multiplying an integral by a negative, you can actually swap the limits around, right? Because at the end of the day, you're going to be subtracting those two limits, and when you put a negative in front of it, it switches a subtraction. So to make it cleaner for us, let's switch the limits around. F of v dv. Now, the moment you have f of v dv, you can replace v with any parameter that you want and get the same outcome. So for example, if you said let x equal to v, then dx equals to dv, and the limits are the same. So in other words, I'm going to replace this guy with 0a fx dx, which we know is the right hand, sorry, I use right hand side here, and that's the left hand side, and that's my proof, right? So guys, that's my proof for this. You know what, I'll leave that. Let's do an example just to really bring this case to life. And basically, when you use this case, the examples where you use this case, there can be little giveaways. Firstly, it's got a limit, right? Not a lot of integrals have limits because the limits require an extra level of working out. So not all of them do. When they do, one of the things you think about, if you can't do it any other way, probably going to be this special case. So let's have an exploration of that. So let me give you an example. Let's do an example just to really see if we can explore this technique. So I'm quite excited after this to then do a few sort of special cases, cool questions sort of thing. So I'll do this part where I said to you, there's part A that says show that. Now see, once again, they're the limits, right? And if you look at this part here, the very fact that they're asking you to prove this, right? I want you to say to yourself that you see that now. Can you see 0, pi on 2, 0, pi? The limits are the same. That usually is a good giveaway that you're going to be using that special case, right? And then sine x plus cos x dx. So that's part A. Yep. So you know, it leads you into part B. So for part B, it goes hence evaluate. Yeah, 0 pi on 2 sine x on sine x plus cos x. Now, if they gave you part B by itself without really saying anything, maybe even without the limits, you probably would consider things like t results, right? Because it's got sine, cos, sine. There's no real trig identity there. But with the limits of especially pi on 2, because I know that there's a relationship between cos pi on 2 minus x and sine, right? So it sort of falls nicely into the formula that we said. Now, I'm just going to go back a slide and copy and paste this formula so I can have it readily available. Just going to paste values. I'll paste that as a JPEG over here, right? So I can shrink it. Yeah, a bit too small. Let's make it big. There's my formula. So it's going to have there. You can see in this question, right? This guy here is going to be my fx, right? As per the formula there. This guy here and this guy here are both values for a, right? So I'm hoping then, if I can prove that this guy is a minus x, right? That's the game, right? So you can sort of see that's my structure. Let's do it. So in this case, I'm going to start with the left-hand side. So for part A, you can't start with the left or right. In this case, it makes absolutely no difference. Yeah. So I'm going to use, right? The formula is usable. Yeah, you can prove it in a question. If this was worth 1 mark, you can prove it. But alternatively, I think this is commonly accepted as a symmetry property, right? So that's absolutely fine. So we're going to use it where I know, right? Just to be clear, once again, this guy's A, right, and this guy here is fx. Then I know this is equal to the same limit. So that's what it says here, right? Equals to the same limits. Yeah, but f of a minus x. So wherever you see an x, replace it with a minus x, so pi on 2 minus x. So that is equivalent to sine, instead of x now, replace that with pi on 2 minus x. Yeah, because this formula is a given, yeah? Cos pi on 2 minus x dx Yeah, a lot of questions, if this was an exam, they actually give you that equivalence, right? The symmetry property upstairs, and then they ask you to use it. But if they don't, I guess we can just use it, right? So sine pi on 2 minus x. So I've just literally just replaced all the x's with pi on or a minus x. Yeah? Now I know, right? I know that sine and cos are complementary. So sine pi on 2 minus x equals to cos, and vice versa. Cos pi on 2 minus x is sine, right? That's all good. So I'm going to use that symmetry to basically say, well, that guy there is cos, that guy there is cos, and that's sine as well. So the top there is cos, that's cos plus sine, which is exactly, sorry, dx, which is exactly what I want because that's the right hand side. Yeah? Is that cool? So pretty straightforward there. Oops, pretty straightforward there. I'll move this one here, just up here, for part A. Now, once you do that, how do we then use the symmetry property, which I've effectively proved, right? How do I use the symmetry property to do part B? Quite easy. And this is quite cool because right now, right, this is the point. It's very hard for me to integrate sine on sine plus cos. It's very hard to integrate cos on sine plus cos. But with the symmetry property, I can actually use it to help me do part B. Now, do me a favor. This always helps, right? So let I equal to the thing that I want to integrate. Yeah? In this case, it makes it much easier for me to do and for me to explain to yourselves. Sine x plus cos x dx. Beautiful. Now, I know, right, that if I equals to this, I also know that from my part A, I also equals to the cos version, right? Because they're equivalent. Yeah, they're equivalent. So both of them are the same. Sine x plus cos x, right? They're both equal to I. So what I'm going to do, guys, I'm just going to almost simultaneously add these two, right? If I add them two, look what I get. I get 2i, right, equals to this guy plus this guy. Now, are you okay? Because they have the same limits, I'm just going to put them both under the same limit, right? So basically sine x on sine plus cos. Can you see where this is going? So put them under the same limit because they both got the same limit. Put it under the same integral. Sine x plus cos x. Guys, if they got the same denominator as well, top and bottom, you got integral, common denominator of that, sine x plus cos x, sine x plus cos x. So I couldn't integrate them individually, but together, sine x plus cos x on sine, that's 1. Right? Integral of 1 dx, which I know it's just x, right? So with the limits of pi on 2 and 0, I know that's just pi on 2. And then, guys, does it make sense? If 2i equals to pi on 2, therefore I, which is what I want, equals to pi on 4. That's how you do it. So by using the symmetry, I say to myself, I can't do these individually, right? I can't do sine on sine plus cos or cos on sine plus cos, but together, when I add them together, I can actually get an integral that's quite simple. That's how you use the symmetry form, symmetry property, right? Or the symmetry case. So I'm now going to just do some random questions that get progressively harder to one of my favorites. The last question, a bit of warning, it's going to be extremely technical, square root of tan x. So let's see if we can get there. So I'll start off with a relatively straightforward one, right? And this one's straightforward, but important. So example, yeah, maybe I'll just go find, and I'll go a integral of, I'll start off easy, right? But still, yeah, good. Just for techniques, right? Now, guys, that's the question. So there's a lot of exponential terms, but this is how you sort of, when you're on top of your integration game, this is what you sort of notice, right? whenever there's a lot of e's, I always say to myself, well, the thing inside the bracket here, if I let this guy be fx, what's the derivative, right? The derivative of this is going to be ex is ex, and then the subtraction comes down, minus e minus x. That derivative is exactly what's upstairs. Yeah, that's good, because if the derivative is upstairs, I'm going to use u sub, right? So if I say let u equal to ex plus, plus du equals to ex minus e minus x dx, therefore dx equals to du minus x, so that's a minus. Yeah, that derivative exactly cancels out, so therefore, so if I let this guy be I, right? Therefore, I equals 2. So that guy is still there. My u sub u into there, I got u squared on the bottom, multiplied by du on the exact thing that would cancel out the thing with x's. So hopefully you guys are okay with the pace that I'm going at. It's just simple u sub, right? And then I get the integral of 1 on u squared, which is going to be -2, so -1 on u plus c. And then last but not least, sub in the value of u. That's my answer. Yeah, pretty straightforward, right? The moment you test that the bottom there has a derivative, which is exactly what's on the numerator, u sub, all right? U sub. Is that cool? So a quick one to get out of the way. Now, I'm going to show you a harder version of this concept, right? And it's common, so bear with me when I try to explain it, because it's a little bit more intense. So integral, let's say 5 cos x plus 4 sine at 22 cos x minus 7 sine dx. Now, so I guess there's a number of ways of doing it. Whenever you see questions where there's sine and cos, where there's no sine squared and cos squared, you can't use trig identities. You're probably thinking maybe I can use t results. Yeah, t results might work for this. Maybe you can use I don't know, other substitution methods. In this case, we're going to try, right? We're going to try. This is what you should always do. Whenever you have a fraction in integration, try letting that be fx, right? See where that takes you. So f dash x, right? The derivative is going to be, now derivative of 5 cos is -5 sine. Derivative 4 sine is plus 4 cos. Now, whenever you get that, you sort of say to yourself, you know what, before I do, maybe I'll switch it around. Yeah? That doesn't look like what's upstairs. Yeah, the minuses on the signs are there. So this is what I'm going to do, right? This is a little hack. If the top can be expressed as a combination of the fx and the f dash x, then I can break that fraction and then integrate. I'll show you what I mean. I'll show you what I mean. Why don't I do this substitution, right? This is advanced. So let's say, so what do I want to do? I'm going to express, right, the numerator of this fraction as a combination of the fx, so 5 cos x plus 4 sine, and I'm going to multiply that by a variable of a plus a constant of a and a constant of b to the derivative. Because guys, what am I aiming to do? If I can find the value of a and b, let's say a and b were nice numbers, and it should be, right? Should be constants. What I'm going to do is I'm going to replace that blue numerator with this combination and then break up the fraction. And the moment I break up the fraction, the first fraction with the a is going to cancel out, just be a constant of a. The second one is going to be b times a derivative on the function, in which case I can use the ln. Can you see that, right? So by expressing as a combination of itself of the denominator itself and the derivative of the denominator, I can split it up and then use my integration skills, right? So let's try to solve this for A, right? So you can do two things. Yeah, you can use simultaneous equations where you basically go, well, I'm going to compare the cos values. Now, where's cos? Will be 5A and then 4B, right? So I can actually go, therefore, 5A plus 4B equals to 22, and then go, well, -7 sine x is going to be A times 4, and then B times -5. So then I get another simultaneous equation that is like 4A minus 5B equals to -7. Yeah, if you solve this simultaneously, right, let's just, cut to the mustard, you will get A is 2 and B is 3, right? Let's see if that works. A is 15 plus 8, no, 10 plus 12, 22, beautiful. 8 minus 15, perfect, right? That's the answer for A and B. Now, what this means, guys, is that my combination now, let's sub in the values of A and put it back into this integral, right? So let's let this integral be I as well. See what we get, right? This is exciting. Therefore, I equals 2. So instead of that blue statement, I got 2A multiplied by the denominator. Great. You know what? I'll put that over the denominator there. And then break up the fraction, right? Plus 3 times the derivative over the denominator. Now, this is great because what happens next is this, right? This guy goes away. I'm left with 2. 2 is integratable, yeah, easily integrable. That's 2x. Plus, now I know, right, this guy here, derivative on function, that's ln, right? So plus 3 times ln of the derivative of the denominator plus c. And I'm done, right? That's how you sort of do this. Now, you can use t results. I've not done it with t results in this question. I'm not sure how long it'll take, but maybe potentially you should get there, but that's a nice way of doing it, right? So whenever you see an addition or subtraction combination of cos and sine, put top and bottom, where the derivative is not exactly on top, try this combination thing where you basically express it as a times the original denominator plus b times the derivative, and then you should be able to get it, right? All right, let's step it up a notch in terms of a little bit of intensity, right? I like this question. Once again, not infrequently seen, so, quite common. Let's see. I like this one because it has a number of techniques, right? A number of techniques. So you may have seen something like this before, dx, right? I like it because there's no start to it. There's no guidance. There's no, can you please use partial fractions or by parts? There's nothing clear about it, right? There's no trig, okay? There's no trig, but then there's square roots, which means once it's like square root of 1 minus x squared, you might want to use some t substitution methods and stuff like that. But there's no start, right? It's very hard to start. So what I'm going to do, right? Whenever there's square roots, I want you to think about this, right? If there's nothing else for you to do with square roots, maybe try rationalizing. Now, in this question, you have the choice of either rationalizing the top or bottom, right? Generally speaking, if possible, right? If possible, so I'm just going to extend this out a bit. Yeah, if possible, try to multiply to the top. In this case, that's plus x, that's minus x. So I have the choice of either, is it going to be 1 minus x or plus x, right? What do I want? In this case, it's plus. Now, why? Because when you multiply the top by 1 plus x, it becomes 1 plus x perfect square. The square root and the perfect square cancel each other out. So you actually get rid of the square root on the top. That's good. Because when the square roots go away on the top, you can actually break apart the fraction. When the square roots get removed on the bottom, you can't really do anything. It's just 1 minus x, you can't. But in this case, by multiplying it by 1 plus x, you get sort of like a double effect. On top, you get the square root and the square cancelling out. But on the bottom, it's the difference of 2 squares. Now, in integration, whenever you see 1 minus x squared, top or bottom, that's actually quite nice. Yeah, because when I break up this fraction, I get a really nice clean sort of or double approach, but it's quite clean in that you can see the first one. You guys recognize it? Technique, right? The first one, sine inverse. The second one, also now 2 different techniques, right? First one, sine inverse. Second one, u sub, right? So if I let u equal to 1 minus x squared, the derivative is on top, right? So I know already this guy is going to be a sine inverse, right? And because the a value is 1, that's it, right? That's really all I do. For this one though, I'm gonna let u, right? I'll do everything off to the side so I have a clean answer. So let u equal to 1 minus x squared, du equal to minus 2x dx, dx equals to du on negative 2x. Right, that cancels out perfect. So what I'm going to do, I'm going to basically go equal to sine inverse of x plus, in this case, I'll split the integral here. That's x on root u multiplied by du on negative 2x, right? Hopefully you guys are okay. The x goes away. And then I will, let's see, bring myself up here. Equals to sine inverse of x. Now there's a minus 2, so I'm just going to go minus a half. And then integrate u to the power of negative half there, du, which equals to sine. Now, when I integrate that, add 1 to the power, right? Add 1 to the power, divide by that new power plus c. The halves cancel out. So in effect, I get square root of u, which is sine inverse minus square root of 1 minus x squared plus c. Beautiful. How's that? Yeah, 2 very different techniques once you get down to it, but it's all about the start. How do you know to rationalize that? Well, practice. And also square roots, right? Square roots, if you're stuck, try rationalizing. And in this case, you actually multiply by 1 plus x because you want to split the top, right? And the bottom just happens to be different to 2 squares, which is quite nice. All right, guys, you know what? I've got one more question, right? And the next one is intense, right? Now, I think I haven't uploaded yet, but I will make an attempt to. Basically, as part of Next Education, my tutoring center, I've put together, like, if you haven't already done so or seen it before, Coronius, the textbook writer, has a list of 100 cool questions for integration, right? If you haven't seen those, please try to, you can easily Google it. Maybe I'll put a link to it. But more importantly, what I've done is basically try to put together the next 100, pun intended, right? The next 100, which is a gathering of 100 very difficult questions. I'll try to put that on the website so you guys can have a download, and when you're in position, you can challenge yourself to it. So in the 100, right, in the next 100, there is a question that looks like this. I think it's question 99, which indicates A, how much I love it, and B, it's actually quite difficult. Square root of tan x, right? So similarly, you can Google this. There's work solutions for this. Let's have a go. Right, now, I like this question because when it's square root of tan x, you're like, is it t results? Is there some sort of fancy technique? You know what? It's u sub, right? Let's just let u equal to that root tan x. Yeah, now, there's going to be a number of times in here where I'm going to take leaps of faith to sort of say, you just have to trust me. This is what you do, right? Do I expect you to be able to see it if you're fresh to this question? Maybe, maybe not. Who knows? But it's not obvious. So step 1, let's do that. Now, we're going to integrate this. So du, now this is almost like a chain rule where the half comes down, right? Minus 1 to the power, and then multiply by derivative of tan, which we all know to be sec squared. Because integral sec squared is tan, derivative of tan. So dx, right? So then which equals to, now if you sort of clean this up, it'd be like sec squared on 2 root tan x dx, right? Already, it's a bit intense, but let's see. Now, that tan x, I've got to swap it around, therefore, dx equals to, times it up, so 2 root tan x du all over sec squared. Now, so that tan x, when I sub it in, yeah, when I sub this guy into here, it won't exactly cancel the root tan x out, but it does turn into tan squared, and I have sec squared. Yeah, tan squared sec squared feels like I can use some sort of trig identity. So I'm going to sub that in, and then replace u with the whole thing. So then maybe let this guy be I, therefore I equals 2, right? Square root of root, sorry, I'll do it as root tan x multiplied by 2 root tan x on sec squared x dx. Clean it up, and you sort of got root 2 tan squared all over 1, sec squared. Now, okay, so if I asked you right now to try to integrate this, right, tan squared on sec squared, not undoable, right? Not undoable. How do you think you should go about it? Number of ways, right? Maybe the cleanest way in this case, let's see, cos squared. One of the cleanest ways, maybe to use trig sub, right? Trig sub here. So let's see. Before I do this, have I done that right? Let's say u times. Yes, u, and that's u squared. Perfect. Yeah. So, so tan squared. Sorry, I'm just making sure that I'm doing it right. Yep, perfect. All right. So let. Oh, sorry. Before I do that, guys, sec squared. We know that. Oh, sorry. The top is not tan squared. That's what I was like. Otherwise, that'd be really easy. It's tan, right? If it was tan squared, it's a really easy question. Yeah. So, but tan is the trick. Now, so what I'm going to do, next step, replace 2 tan with 1. So replace sec squared with 1 plus tan squared. Now we're getting places, guys. Now we're getting places. So in this case, can I ask a favor, right? And I'm going to do it still with the u in here, right? I'll do it still with the u in here. Can I sub this u back into here to actually try to break this down? Check this out. Check this out. This becomes 2u, 1 plus. Now, if root, so u squared, right? If tan is u squared, then this must be u for du, right? Yep. Is that all right? So let's see where this takes me. Now, okay, I can get there. Guys, this here requires a little bit of faith, right? How do you know to do the next bit where I'm going to just divide top and bottom, right? So I'm going to try to complete the square here to make it look a little bit, sorry, not even complete the square. I'm going to split this guy up into 2 parts. Can you please replace this with u squared plus u squared, right? Actually, can I leave a space here plus u squared? Because at the same time, if it's okay with you, I'm going to plus 1 and simultaneously minus 1. So I'm going to turn this guy into u squared plus u squared and then add 1s on both sides, right, to get it to look like this. U squared plus 1. Yeah, and I'll split the integral. U squared minus 1. Yeah. Now, okay, check this out. I am going to divide top and bottom, divide everything by u squared. Okay, you're going to have to follow me on this journey, right? It's one of those questions where persevere, see where it takes me, right? So on top, I'm going to get 1 plus 1 on u squared. You know what? Can I rearrange the... no, that's absolutely fine, actually. 1 on u squared. And on the bottom, I'm just going to rearrange the order here. I get u squared plus 1 on u squared du plus, and on this one, I get 1 minus 1 on u squared on u squared plus 1 on u squared. Now, where am I going with this, guys? I'm going to try to use the fact, I'm going to try to somehow manipulate the bottom now to make the derivative appear on top, right? So once again, check this out. So do I have much space? Yeah, I got a little bit of space. A bit of manipulation, check this out. In this situation, I'm going to try to complete, so you, just off to the side here, right? You guys know if I expand, let's say, instead of u, maybe I'll go x plus 1 on x, right? Squared. What's that give me? It gives me x squared plus, now, the importance of having something, a variable with its reciprocal is that 2 times this gives me 2. There's no more x's in the middle, plus 1 on x squared, right? And similarly, if this was a minus, the only difference is that that's a minus. Now, why am I telling you that? Because you can sort of see, in this case, the u squared plus 1 on u squared is like saying this, right? So if I put a square there and a square here, the only thing that changes is that becomes a 4. That becomes a 4, right? So what I'm going to do, guys, is, actually, no, sorry, I lie. So forget about the square. So you can sort of see u squared, 1 on u squared. That's like this guy and this guy, right? So to complete the square, I need to add 2 or minus 2 if I wanted it to be a minus, right? This is what I'm going to do. For this one, because it's a plus upstairs, I'm going to complete the square with a minus. I want a perfect square with a minus because I know when it's reciprocals, the derivative of a reciprocal makes it plus. I'll show you what I mean. Now for this one, I'm going to minus 2 and then simultaneously add 2, right? I'm going to complete the square with a minus. Yeah, bear with me. If that's a plus, complete the square with a minus. For this one, when it's a minus, complete the square with a plus. You'll see why in a second, right? And then minus 2. All right. Now, the moment you get that, let's see, right? It's a bit intense. Bear with me. The mass is great, but not overwhelming, hopefully. Now, this perfect square becomes u minus 1 on u squared, just like I did up here when that's a minus, right? By adding in a minus in the middle, you get that plus 2 du plus integral 1 minus 1 on u squared u plus 1 on u squared minus 2 du. Now, this is the plan, right? I'm going to u sub both of these because if you think about it, if I let u equal to this, the derivative of this is 1. And because this is u power of minus 1, when I differentiate, the power comes out, it's a plus 1 on u squared. It's actually the top, right? Whatever's on top is the derivative of this guy. So u sub absolutely works. And the same deal here. If I let u sub be that, right, let it be another letter, the derivative of this is going to be 1. This guy's a reciprocal, so it'll be negative u to the power of negative 1 minus 1 down. You get exactly the derivative upstairs. So this also hangs together. So guys, I'm going to split this fraction into 2. Right, let me park this theory up here. Right, draw a straight line. So for this guy here, right, I'm going to say now I've already used u. Let's use v equal to u minus 1 on u. Sorry, I'm going to zoom in. Right, where I know then dv equals to 1 minus, let's just cut through it, right? 1 plus u squared du, right? That's nice because then du equals to dv 1 plus u squared, yeah? Which exactly cancels out with its numerator. And then similarly for this guy here, if I let w equal to u plus 1 on u, dw equals to 1 plus, now because it's plus, it'll be minus 1 on u squared du, and du then is dw over 1 minus 1 on u squared. Perfect. Double sub. So therefore, my integral equals to, right, If the u goes in, so let's just cancel it out. It becomes like 1 over v squared plus 2 dv plus integral. Yep. Now there's a lot of substitutions here. I will substitute it back in later. Minus 2 dw, right? All right. Now that we're here, hopefully you guys are on top of your techniques, right? I know. For this guy, that's tan inverse, right? When it's a plus tan inverse. Does anybody remember? Do you guys remember? What happens when it's a minus? W squared minus 2. Yeah. Now, it's ugly numbers, but I can actually factorize that into difference of 2 squares and use partial fractions. You know what? Off to the side, whenever you have integral of a difference of 2 squares of 1 minus x, or x squared minus a squared, dx. So squash it in. There we go, dx, right? As a shortcut, if you wanted to do this by partial fractions, feel free to, but the shortcut would be it's 1 on 2a ln x plus a on x minus a, plus c. That is a shortcut for it. Now, so when you do this, let's just use, for the blue, let's use tan inverse. For the red, let's use a shortcut where the blue, it becomes tan inverse is 1 on a tan inverse of v on a plus c. For the red, it will be 1 on a, so 2 root 2. Yep, ln w minus root 2, or plus root 2 rather, on w minus root 2. Guys, plus c. Last but not least, let's sub everything back in and get it back into an expression with x, where sub in your substitutions that you did for v and w, and then sub in your substitutions for u, right? So we got a double substitution step left, where it's 2 tan inverse. Instead of v, it's u minus 1 on u on root 2. Yeah, and instead of w, it's u plus 1 on u plus root 2 on u plus 1 on u minus root 2 plus c. Yeah, and if you're really cool about it, you would then substitute all your x values back in. So I wonder if I can shift this up a bit so I have the vertical space to do so. Perfect. It gives me one line to do so. So I know that u was root tan. So let's do this here. Yep, so let's see. Equals to 1 on root 2 tan inverse. Yep, root tan minus 1 on root tan all over root 2 plus 1 on 2 root 2 ln root tan. It actually cleans up a bit nicer. And I'll see if I can fit it in here. Plus root 2 all over root tan, running all over my logo. It's fine. Root tan minus root 2 and plus c. All right, let me see. Do I actually have the solution that is clean? Oh, I think, yeah, the only thing that they do is they put it, some answers have that as cot, but that's my answer. Hot damn, right? So when you get exposed to square root of 10, this is the approach. It's like substitute it with u. Yeah, get it to a point where you're going to have to complete the square. Now, how do you know to complete the square? I think when you're working through this, whenever you get a fraction, the aim is to always try u sub. And in this case, the reciprocal relationship between u squared plus 1 on u squared and 1 plus, it's a derivative, right? If you can complete the square. Once you do complete the square, we got the blue box and the red box, which is done by tan inverse and partial fractions. Guys, hopefully you enjoyed that video. A few special cases, a few cool questions. I'll try to link in, probably not immediately, but I'll try to link in Coronius's 100 and also the next 100. Feel free to share it with your friends. If you like this video, give me a like, subscribe. I'll see you later.